Okay, welcome everyone to the final DIMAP seminar of this term. So it's my great pleasure to introduce our speaker today, Bart Jansen from University of Eindhoven. So Bart is a well-known expert in graph algorithms, in parameterized complexity, and especially in the sub-area called kernelization. Bart has a very nice track record of excellent work in these topics. Plus, he is the PI of an ERC starting grant. So today he'll talk about a very recent exciting result on vertex deletion parameterized by elimination distance. And that's not all. He will also talk about something parameterized by elimination distance and even less. So, but a warm welcome to Warwick, at least a virtual welcome. And whenever you're ready, feel free to start.
Great, thanks a lot. It's my pleasure to be virtually in Warwick. I'm presenting joint work with my PhD student, Jan de Kroon, and postdoc Michał Podaszczyk. If at any point in the talk you have questions, feel free to put them in the chat. There's a small window on the side of my screen where I'm trying to keep my eye on it. You're also happy to interrupt me if something is not clear. So what I'm going to do is to talk you through the motivation of this work. And in due course, we will also see some very concrete ideas which would suit your discrete math seminar very well when it comes to solving various vertex deletion problems with new types of complexity measures that we've talked about before. The full paper is on arXiv if you're interested, but I have to warn you, it's long. It's at least 70 pages, so I'll be cutting quite a few corners here and there. Good. Let's start with the setting. We're looking at vertex deletion problems, where the thing we want to achieve after having deleted a certain set of vertices is that now the graph we end up with belongs to a certain graph class, which we denote by H. And we'll be doing this for input graphs which are undirected. And it turns out that many of the well-known NP-hard graph problems can be phrased in this way. To give you some examples, the vertex cover problem is traditionally defined as find the smallest vertex set that contains at least one endpoint of every edge, but you can also think about it as delete me a vertex set such that afterwards the resulting graph is edgeless. There's the feedback vertex set problem, which asks to delete vertices to get an acyclic graph. There is the odd cycle transversal problem. We are transversing all of the odd cycles, which effectively means that we're deleting vertices until the graph we are left with is bipartite, so the graph should have a proper two-coloring. And maybe as a last example, there is a problem called Chordal vertex deletion, where we're deleting vertices from the graph to get one that is chordal. So in the resulting graph, whenever there is a cycle of length 4 or more, that cycle should have a chord, as indeed this one does. So the first two here are among CARP's original 21. The other problems have lots of applications in data cleaning, deadlock prevention, process monitoring. There's even a recent paper that shows applications of odd cycle transversal to mapping problems onto current quantum computing architectures. So there's lots of applications for these problems, but we're in it mainly for their fundamental nature and the algorithmic techniques that we discover when we start looking into them. So all of these problems are NP-complete by the classic results of Lewis and Yannakakis, and therefore we need some way to cope. We can consider approximation algorithms for these problems, but that's not what we're doing in this talk. We're looking at fixed parameter tractable algorithms. Fixed parameter tractability, maybe as a refresher, it's a framework to deal with NP-hard problems. We assign to every input some complexity parameter that we know by k, independent of the total size of the input graph or its number of vertices n. And then we ask ourselves, is it possible to find an optimal solution to the problem in time that scales possibly by some exponential function f, the parameter, but polynomial in n? And as soon as you turn to this type of algorithmic analysis, the question becomes, what is the right complexity parameter to use? A very natural choice for a lot of problems is to use the size of the optimal solution of the input as a complexity parameter. And effectively, what you're then doing is you're trying to answer the question, if my input graph is large, but the optimal solution is small. Can I find it efficiently, yes or no? And if so, how should the algorithm go about doing it? And for the 4 problems down below, the answer to each of these is yes. You can find a vertex cover in time 1.27 to the power opt times a polynomial in n. Feedback vertex set, odd cycle transversal have similar looking running times, and the Chordal vertex deletion problem is also fixed parameter tractable, but here it's not a constant to the power opt, but 2 to the power opt log opt. In any case, you can think of all of these as being algorithms that show if my input is large, but its solution is small, then I can find it efficiently, even though it is an NP-complete problem. However, these guarantees are really not very useful if the size of opt is proportional to n, because then running times like we have here are really not much better than a trivial solution, which we try all subsets of the vertex set and see which one of them is the smallest deletion set that works. Okay, so on the one hand, we have a paradigm here which has been very successful in the analysis of graph problems from the parameterized complexity point of view. On the other hand, we see that on inputs with large optimal solutions, their guarantees are not so useful. There has been an alternative line of research, and that is not to look at the size of an optimal solution to the vertex deletion problem as the parameter, but to use some complexity measure of the graph. And one way to measure how complex a graph is could be, well, how tree-like is my graph? If the input graph really is a tree, then many of these problems can be solved efficiently. And there are various width measures developed, including tree depth and tree width, which somehow express that your input graph is well-behaved or structured in a tree-like fashion. And when your graph is well-behaved like that, then for lots of problems, you can find efficient solutions. For example, the vertex cover problem can be solved in time 2 raised to the tree width of your graph. Feedback vertex set needs a 3. Odd cycle transversal similarly, and also the Chordal vertex deletion problem can be solved in time that's fixed parameter tractable in the tree width and polynomial in n. Okay, so this is a separate branch of developing algorithms, and these algorithms are good when your graph is tree-like, but well, what if your graph is not tree-like? So that's when we come to the aspect of hybrid problem parameterizations. Basically, we try to find algorithms that combine the best of both worlds. On the one hand, we had algorithms which are good when the optimal solution is small. On the other hand, we had algorithms which are good when your input graph is tree-like, and we combine both. So we use a new way to measure the complexity of an input. It's never going to be larger than opt. It's never going to be larger than these width measures that were studied before, and they can be arbitrarily much smaller. And we're going to develop fixed parameter tractable algorithms to solve the vertex deletion to the target class H problem with these types of parameterizations. So at a very high level, the algorithms we develop, they mix the best features of both these types of algorithms. On the same one hand, they are going to exploit properties of the first type of algorithms in those regions of the graph where the solution is small. And they're going to exploit maybe tree-likeness or having small tree depth or tree width in regions of the graph where the solution may be large, but those regions are not so difficult in terms of structure. So to get such algorithms, basically we take a two-phase approach. We first define new types of decomposing an input graph, where the decomposition actually depends on what is the vertex deletion problem that you're solving. And then we're using those decompositions to solve the vertex deletion problem. So to be able to tell you what the problem parameterization is that we use, I'm going to have to define you these decompositions, which I will do in a minute. In the meantime, if there's any questions, now would be a good time, and I'll keep my eye on the chat. Good. So let me define you the tree depth notion of a graph, because we will use it as a starting point for a new type of problem parameterization. The tree depth of a graph, it has many names. It has also been known as the vertex ranking number, and there's equivalently many ways to define it. but here's the definition that's currently my favorite. I take a graph, and to define its tree depth, I look at the following process. I'm going to do a number of rounds. In every round, I get to delete one vertex from each connected component, and I'm done when the graph doesn't have any vertices anymore. Now I ask myself, what is the smallest number of rounds I need to clear the entire graph? So, for example, if we can start by eliminating the vertex in the middle, that will be round 1. Afterwards, we have 3 connected components left, and that means that in round 2, we get to pick one vertex from each of them. Then, in round 3, we pick one vertex from each connected component, and in round 4, we have succeeded in clearing the entire graph. Okay, of course, it's not so easy to see which vertices you should pick to get the minimum number of rounds in total. Different choices would have led maybe to the process finishing later or earlier, but this is what the definition says. And you can represent the sequence of choices that you made when eliminating the graph into a tree-like structure. So what I do is the first vertex that was eliminated from the graph, I draw it at the top. In the next round, I eliminated one vertex from each component. I draw them as children. For each component, I eliminated a vertex in the round after. I draw it as their children. So the lines in orange represent basically the tree structure of the rounds. And now you see that the actual edges of the graph, which are drawn in black, they only connect vertices to ancestors in the tree, because they correspond to vertices in the same connected component which were eliminated at an earlier point in the process. If we have vertices that ended up in different components, then they will belong to different branches of the tree. And since there are different components, there's no edges between them. Okay, so we can think of the tree depth of the graph as the minimum number of rounds to eliminate all of its vertices. And equivalently, we can think of it as this elimination forest that encodes the elimination sequence, and the number of layers in this tree is effectively the depth of the forest, which corresponds to this tree depth value. And intuitively, having a small value of tree depth measures how star-like your graph is. If you really have a graph that's a star, then its tree depth will always be 2. If you have a graph that has a very long path, it will not be star-like and it will have a large value for its tree depth. Okay, so this is an established concept and it's being used in the design and analysis of parameterized algorithms for a while now. Let's look at a related concept, the elimination distance to H, where H here is a graph class, like bipartite graphs or Chordal graphs. And it's defined by a similar process in rounds. So now we are starting with an input graph G. In every round, we again delete one vertex from each connected component, but the process stops as soon as the graph we're left with belongs to the target class H. So if our target class is that of the bipartite, we can start by eliminating this vertex here. Our graph splits in 2 components. And if we then select one from each connected component and remove it, the resulting graph is bipartite. So now the elimination process stops, and in 2 rounds, I managed to make this into a bipartite graph, which is noteworthy because if I wanted to make this into a bipartite graph by just deleting vertices one at a time, I would need much more than 2. Right, so I can label each vertex that got eliminated by the round in which it was eliminated, and then again I represent the elimination process by a tree structure where children are assigned based on rounds that followed the previous one. And instead of having a single leaf to this tree, I will consider the entire subgraph that is a connected component of what I'm left with when the process ends. One such connected component, I call it a base component, and I think of them as being the leaves of my decomposition. So I have a tree here with 3 layers. The first 2 layers have individual vertices, and the last layer has connected subgraphs of the input, which I call base components. And then the elimination distance of your graph until you get to graph class H is the minimum number of rounds, or equivalently, the minimum depth in a forest, which has as its leaves these connected components that belong to H. And as I alluded to earlier, this elimination distance is, on the one hand, never larger than treedepth of the graph, because in this process of defining it, we get to stop earlier. We can stop as soon as the graph belongs to our target graph H. And it's also never larger than the number of vertex deletions you would have to do to get to H. Because if you know a set of vertices whose removal gets you a graph in H, then removing all of them in one round each ends up with your target class. So this is a parameter that is not larger than the optimal solution value of your deletion problem, and also not larger than this measure of star likeness captured in treedepth. Let me tell you a little bit about prior work on computing the treedepth and elimination distance values. The treedepth can be computed exactly in time 2 to the order n. There's also a fixed parameter tractable algorithm for it. And there are also polynomial type approximation algorithms to, given a graph, compute an elimination forest encoding this sequence that eliminates to an empty graph in polynomial time. And this is a poly-opt approximation. When it comes to computing the H elimination distance of a graph, where you can stop as soon as your intermediate graph belongs to H, there's been a lot of work in the recent months and years. The concept was first applied to parameterized algorithms by Bullion and Dewar, who use it as a parameterization to solve the graph isomorphism problem. And in their work, they showed that when H is a class of F-minor free graphs, you can compute this distance exactly. And when H is a class of bounded degree graphs, they gave an approximation algorithm. There's an exact algorithm for bounded degree graphs with planar inputs from last year. MSR, in part of his work, also worked on graphs which are cluster graphs with a certain elimination distance. With my student Jansen, co-author of the paper, we looked at bipartite graphs. There's been work for target classes which have constant rank width. And in stacks this year, there was a general result that said that for a large family of graph classes, as long as you can define them by giving a finite set of forbidden induced subgraphs, then you can compute the H elimination distance to this class in time that is, on the one hand, fixed parameter tractable, but on the other hand, the function f is quite daunting. It's not a single exponential, but a bit worse. Let's leave it at that. So this is what was previously known on computing treedepth and elimination distance, and using this terminology, I can now tell you what we did in this paper. So we looked at vertex deletion to H for various graph classes H, and then we obtained 3 types of results. On the one hand, we gave new decomposition algorithms. So we gave algorithms that, given a graph with a certain elimination distance to H, they output you an H elimination forest, basically an elimination sequence. And the depth of this elimination forest is polynomial in K if the optimum is K. So these are poly-opt approximations that run in fixed parameter tractable time. And in many cases, the fixed parameter tractable dependence is 2 to a polynomial in K. So significantly faster than earlier approaches, at the expense of being approximation algorithms, of course. So this works for a range of target graph classes, including the ones that I've shown you on the first slide, the target of bipartite graphs, Chordal graphs, planar graphs, but also families defined by a constant number of forbidden connected induced subgraphs, or forbidden connected minors, or forbidden connected topological minors. So in quite some generality, we were able to find decompositions that basically compute H elimination distance. Then what we were really after was solving the vertex deletion problem. So we also show that once you have an elimination forest that encodes the elimination sequence, you can use it to optimally solve the vertex deletion problem to H. And to do this in time, again, that is polynomial in the dependence on the parameter in the exponent. So this works for almost all classes for which our decomposition algorithms work, but not quite all of them. And then finally, we also gave hardness proofs. So there's some graph families that we would have loved to add to our list of positive results, but we didn't manage. And then we found proof that that is actually impossible. So if you would like to end up with a perfect graph, one where the graph coloring number is identical to the click number, then these type of FPT algorithms do not exist, not even approximate FPT algorithms. So this was a technical perspective, but for me, what is most rewarding about this process is that these results gave me a new way to think about tractability and what can be efficiently computed when it comes to answers to NP-complete problems. So I think the mindset that at least I had of solving vertex deletion problems exactly used to be the following. It used to be you can only solve inputs where you know either that the solution is small or the input graph is tree-like. And otherwise, it doesn't go. As a sort of high-level message of our results, to me, they've really broadened up the space of inputs for which we can provably find a solution efficiently and exactly. So whenever you have an instance of a vertex deletion problem, that maybe it has large optimal solutions, maybe also its tree width and tree depth values are large, as long as its elimination distance to a graph in the target family is small, then you can provably find an optimal solution quickly. So it's not just that we should think about easy inputs as one that have small optimal solutions. Easy inputs are ones that have small elimination distance, and maybe the story doesn't even end there. So maybe a little bit of background. The wide applicability of these techniques came somewhat as a surprise for me. So we initially looked at this for the problem Odd Cycle Transversal, and in fact, many of the examples I will show you are for Odd Cycle Transversal, where it seems to be sort of a fluke, a happy coincidence that there things work out. But it turns out that actually for a lot of other vertex deletion problems, the same type of parameterization leads to tractability, to the point where currently, if you had to ask me, I would say that in general, if the parameterization by solution size is fixed parameter tractable, I would bet at least $100 that the elimination distance parameterization is also fixed parameter tractable. Good. So in the remainder of my time, I want to give you, on the one hand, the outline of how we go about our two types of results, but also some details when it comes to bipartite graphs, because there's some nice combinatorics that pop up there. So the first results we have are about approximating this H elimination distance, and let me start there. The high-level idea is as follows. As I showed you in related work, there do exist good algorithms to compute or approximate the tree depth of a graph. Right? And tree depth is sort of related to H elimination distance because it can be defined in terms of the number of rounds, but it behaves quite differently to the extent that if you apply an algorithm for tree depth directly, it really doesn't tell you anything useful about the H elimination distance for various classes H. To give you an example, here's a graph, and you should think of this as being an arbitrarily large grid. So a grid is a bipartite graph. This graph has elimination distance 1 to being a bipartite graph, right? As soon as we get rid of this vertex, the remainder is a bipartite graph. But the tree depth value of this graph is arbitrarily large. The larger of a grid you put here, the larger the tree depth becomes. Because if you want to eliminate the grid to the empty graph by doing one vertex deletion in each round from each component, well, it's hard to break up a grid. That's the intuition. So really, computing the tree depth of the input graph as is doesn't tell you anything meaningful. So here's the important idea. What we want to do is take our input graph. We're going to define a contraction of it by contracting certain vertex sets into single vertices. And what we want to achieve is that the tree depth of our contraction starts to behave like the elimination distance of our original graph to the class H. Let me show you a picture to aid the imagination. So suppose that we start from the same graph as we just had, which was one elimination round away from being bipartite. Suppose that we partition this graph into connected vertex sets, visualized here in terms of colors, and then we contract each of these color classes into a single vertex. And now we see that this entire bipartite grid, it got contracted down into a single vertex, which means that this resulting graph, it has a small value of tree depth. This graph has a tree depth value of 3, which is much closer to the H elimination distance value of the original graph, which was 1. Right? So the goal now is to, in general, be able to define a partition of the vertex set of the graph such that the corresponding contraction satisfies this approximately. So on the one hand, we want that the tree depth of the contraction should not be large in terms of the H elimination distance of the original. So we want to contract things sufficiently to make sure that the tree depth of the contraction becomes small. On the other hand, the tree depth of the contraction should still represent something meaningful because we want to also be able to go in the other way. If we manage to compute the tree depth of the contraction encoded by some elimination force, then we want to be able to lift back the elimination sequence of the contraction into an elimination sequence of the original, which doesn't end with the entire graph being cleared, which ends at least with every component belonging to our target family H. So the first point means we want to contract sufficiently to get the treedepth value down. The second point says we want to contract wisely so that an elimination force of the contraction can still be lifted back to turn it into an H elimination sequence of the original graph G. So what do we want to achieve to make sure that the tree depth of G prime becomes suitably small? Well, intuitively, what we know is that the original graph has some H elimination distance, and after you eliminate the graph, we have these base components left. If there are base components whose tree depth is large, we basically want them to be contracted to small vertex sets, such that if you look at what the elimination sequence would do to this graph, when it stops with certain base components left, we want those to have become contracted into a small number of vertices, such that if you eliminate those as well, then your entire graph is cleared, showing that the tree depth is bound. To go in the other direction, we want to make sure that if I contracted a vertex set into a single vertex, then the thing I contracted, for example, here I contract the entire yellow set, and I want the thing I contract to basically correspond to a graph that belongs to my target family that lives here, and it has a small neighborhood in the same color class that lives here. So basically every color class I contract, I want it to consist of a graph in my target family together with a neighborhood, and the neighborhood size should be small in terms of the elimination distance of the graph. Why is that useful? Well, if I know that all the sets I contract have this form, and I have an elimination sequence for the contracted graph, then whenever it tells me to say, eliminate the red color class, I could mimic it here by saying, I eliminate the neighbors of my C, and then the actual component C is allowed to stay in the graph because it belongs to my target family. And if I've eliminated all of its neighbors, then it doesn't connect to the rest of the graph anymore. So that would be allowed in an elimination sequence that ends up with a graph in H. And that's the motivation for having these two sort of conflicting goals, but it's something that we will see how to achieve. And it turns out that to achieve both of these goals, we are led to study a new type of graph separation problem, or at least a version that has a small twist compared to what's usually done in literature. So to satisfy the second condition that we've just seen, the following type of separation problem comes up. We call it H separation, where H is again our target graph class. Think bipartite graphs. So what does an input to this problem look like? As input, we get an undirected graph G, some integer k, and a connected vertex set Z. And here Z consists of these three vertices. What do we find as the output? We want to compute a connected vertex set we call C. On the one hand, this set should belong to our target class H, and it should have a neighborhood in the graph that is bounded size in terms of k. See how this corresponds to the condition I just put on the second item to be able to go back from the tree depth of the contraction to the H elimination distance of the earlier one. This is basically finding one vertex set which would be fine to contract into a single piece. If we look at this input, then we can see that on the one hand, the graph has some odd cycles, which are not allowed to be contained in our vertex set C. And we also want the neighborhood of our C to be small. So it turns out that taking the inside of this blue curve, this would be a valid solution because this induces a bipartite graph. There's no odd cycles in this part of the graph, and it has a neighborhood of size 2 living here. Okay, so I hope that this clarified what the H separation problem asks you to do and how it connects to this high-level intuition of the previous slide. So we study this problem for various classes H, and we get FPT and approximation algorithms for this problem. And there's a variety of different techniques involved. Maybe you've heard of them: importance separators, the Erdős-Pósa packing versus covering duality, some bounded depth branching algorithms, min, cut, max, flow. And it turns out that there's a very high-level connection between, on the one hand, being able to solve this separation problem, and on the other hand, carrying out this high-level idea I just discussed to compute the H elimination distance approximately. And this high-level connection is formalized into the following level. If you have an algorithm that solves this H separation problem in a certain running time that depends on n and k, it might be a polynomial in n and an exponential in k, and that happens most of the time. It might also just be a polynomial in n and k. If you manage, then you can black box translate this into an algorithm where you give it a graph G that has a certain elimination distance to your target family of k, and it outputs you an H elimination forest whose depth is on the order of k cubed log k. So this is a poly-opt approximation to computing the H elimination distance, and it does so in basically polynomial in n overhead over whatever the running time was of your black box. If your black box was in polynomial time, then actually the overall algorithm will be in polynomial time. And this carries out the intuitive process of using calls to this subroutine to define a contraction, approximating the tree depth of the contraction, and lifting it back using the structure of the vertex sets that you contracted. If that rough idea is clear, then now I want to show you some hands-on combinatorics to see how you can actually do this when your target class is that of bipartite graphs. So now we are in the setting where we want to end up with a vertex set that induces a bipartite graph, and we're looking at an approximate version of the problem where instead of saying the neighborhood of my bipartite subgraph should have size k, it's fine if the neighborhood size is up to 2k, or if you report that it's not even possible to do it with a neighborhood of size k. So there's basically a factor 2 approximation in what the size is of the neighborhood. And if there is a set that has a neighborhood of size k, then the algorithm will find one that has a neighborhood of size at most 2k. And we will see that to solve this problem, actually, we can reduce it to finding a minimum ST separator in a version of the graph that somehow encodes the parities. Let's see how. On the left, I will have a sketch of what's happening and a proof by example. On the right will be the formal steps that the algorithm would go through just to make sure that it's self-contained and actually not all that long. So let's see how we approximate this bipartite separation problem. To start with, if it's at all possible to find a superset of Z that forms a bipartite graph, well, then Z itself should form a bipartite graph, and we can compute some two-coloring of it greedily. So let's do that. There's a two-coloring of the set Z into classes A and B. Then we can use this to create a copy of the graph that is going to encode parities, where parities will be important because being bipartite is equivalent to not having odd cycles, so the odd-even parity will be important. What is our parity graph? Well, for every vertex of the original, we're going to make two copies, a yellow and a green one, corresponding to two parities. Whenever there was an edge between two vertices in the original, we're going to put two edges. Only those edges between the opposite parities will go into our graph. And I've drawn the graph in such a way that the edge crossings are mostly legible and they will make sense in a minute. Let's see what we can do. So we're going to also define two vertex sets in our parity graph. Basically, for every vertex that was originally in Z, the thing we wanted to make a superset of, we put it either in S or in the T side. And there is an exact definition written on the slide, but intuitively, what you can say is we start by putting one vertex in the set T. And if you walk through the bipartite graph, then you know every time you take a step in the bipartite graph, the parity switches. So we let T consist of what you can reach from this bipartite graph when switching parity with one go, and S consists of all the parity twins of the vertex set. Okay, and now let me observe the following. If we start at a certain vertex of our graph, and we take a number of steps which stay within a bipartite subgraph of the original, then we know that every time we take a step in a bipartite graph, we switch over to the other partite set. So if we take a walk through a bipartite subgraph and arrive back at the same vertex, then we arrive back at the same parity, right? Which means that if we start from this yellow copy and we walk through the bipartite subgraph, we again arrive back at the yellow copy. But if we look at an odd cycle in our graph, remember there was a triangle over here, then we can use a triangle to switch parities. If I start in the yellow copy and say that I walk over edges until I get to the odd cycle, here I can traverse the odd cycle, and now on my way back, I have switched parities so that I can actually come out at the other parity copy of T. So here you see that if you can reach an odd cycle, you can use it to switch parity and go back to the other parity copy of yourself. And this shows how this parity graph basically encodes whether or not odd cycles are reachable, because whenever an odd cycle is reachable, you can use it to go to the opposite parity copy of yourself. And that is essentially how we're going to transform this problem into a minimum cut problem. So we're going to compute a minimum ST separator in this graph for S and T as defined here. We know by Menger's theorem that its size is equal to the number of internally vertex disjoint ST paths. So here there's two internally disjoint ST paths and a separator of corresponding size 2. And why is this a separator? Well, if you look carefully, you'll see that the layer that has T sort of floats on top and has no more edges to the layer that floats behind. So there's no edges from S to T anymore. And now we inspect this separator. If the size is more than 2K, then we fail. We claim that having a neighborhood of size at most K for a solution is impossible. And if the separator in our parity graph has size at most K, then we see, okay, which copies did you take, which vertices did you take a copy of in the separator of your parity graph? That same vertex set we remove from our original graph, and then we see what is the connected component that Z ends up in. And in this case, we see that here we get this connected component that contains Z, and it's precisely the solution that we wanted in this problem. So in this way, we can reduce the problem to finding a min-cut in a graph, which is solvable in polynomial time by min-cut max flow techniques, which means that given a graph that has elimination distance k to be bipartite, you can actually find a corresponding bipartite elimination forest in polynomial time. And this will be a poly-opt approximation to your bipartite elimination forest. Good. Let's take a breath. That was the detailed sample I wanted to give you of computing the decomposition, the acyclic elimination distance, and the key point was to see this connection to the corresponding separation problem, which in case of bipartite graphs we can solve with min-cut max flow. Now I also want to spend some time on what do you do once you have such a decomposition. If you know an elimination forest that encodes this elimination process until you get to a graph in your target family, how can you use that elimination sequence to actually solve the vertex deletion problem that you started with? And here again, I want to give you some in-depth combinatorics for one particular problem. And again, it's going to be the odd cycle transversal problem, where I show you how this goes. contrary to the previous case, it's not the case that odd cycle transversal is an instantiation of the general principle. There is some lucky fluke that happens to work for odd cycle transversal, but it doesn't go in general, and that's why I tell you the details of the, say, lucky fluke first, and then I'll show you one slide about how the general mechanism works. So what we're going to be interested in is we have an elimination sequence that ends up with a bipartite graph, and now we want to use it to find a minimum odd cycle transversal. And we're going to use a polynomial time subroutine, which is inspired by the algorithm of Reed, Smith, and Vedda for solving odd cycle transversal parameterized by the solution size with iterative compression. And even if you've seen the original algorithm, maybe this subroutine is phrased in a way that isn't like the one you've seen before. So let me talk you through. We're going to look at a subroutine where as input we get a bipartite graph. Its color classes are V1 and V2, V1 on the left, V2 on the right, and each vertex comes equipped with a list of allowed colors, which is a subset of 1 and 2, because we're going for 2 coloring. Then what we can do in polynomial time, we can find what the smallest vertex set is that you have to throw out of your graph, such that everything that you have left has a proper 2 coloring that actually assigns each vertex a color from its list. So this is basically find the smallest number of vertices so that the remaining graph has a proper list coloring. And again, this turns into a min-cut max flow type of computation. So let's see why. The formal definitions are here, but let me start by pointing out why these should make sense. Suppose that we have a vertex on the left that is not allowed to get color 2, so it's forced to be color 1. And we have another vertex on the left, which is forced to be color 2. If these two vertices end up in the same connected component of G minus S, the coloring will be impossible, right? Because within one connected component, as soon as you fix the color of one vertex, then this will propagate to also imply what the coloring of all the others will be. In particular, if these two vertices both appear on the left, there is an even length path between them, which means they should get the same color in any 2 coloring. So if they're forced to opposite colors, then any solution will have to separate them. Similarly, if we have vertices which are forced to the same color, but they appear on opposite sides of this bipartite graph, then if there remains a path between them in G minus S, then this path basically forces a switch of color every time you traverse an edge, which means that if the vertex here is colored 2, then this one is 1, is colored 2, is this one is 1. So as long as these two, which are both forced to be colored 2, remain connected, such a coloring is impossible. Which shows that if you generally define vertex sets like here, you can show that a vertex set S is a solution to this problem exactly when there's no path from X minus S to Y minus S anymore after you remove the set S. So here we can make a separator by removing this vertex and removing this vertex. Then we break all the paths between red and blue, and in the corresponding graph, you can find the 2 coloring that satisfies what you want to do. So you can solve this problem by finding a minimum separator separating the vertices from X from the vertices in Y, where this time around the separator is allowed to delete from the sets X and Y. Previously, it was not. Good. So luckily, once we have this subroutine, the algorithm to solve odd cycle transversal is not all that difficult, and it fits on the following slide. So instead of solving the odd cycle transversal, we're going to solve something slightly more general. We're going to look at the version inspired by what we've just seen, based on list coloring, where we get a graph and a list of allowed colors for every vertex. The goal is to find a smallest vertex set whose removal makes sure that there appears a 2 coloring that respects the list. And if initially you give everyone the list of both 1 and 2, this exactly captures odd cycle transversal. Now, if we are given an elimination forest that reaches a bipartite graph after k rounds, we can use it to find a minimum odd cycle transversal and to solve this generalization as follows. If the input graph is disconnected, then there's no interaction between the connected components, and we can separately solve the problem on each component. If the input graph happens to already be bipartite, which in particular includes the case that the elimination distance is 0, then this is exactly an input to which we can apply our subroutine, right? Then we can solve the problem in polynomial time. So if G is not disconnected and G is not bipartite, it means that it's a connected graph, and this elimination sequence starts in the first round by eliminating one vertex. Let V be this vertex. And then we're going to recurse on 3 subproblems. It might be that in an optimal solution to the input, vertex V ends up being deleted. To catch those types of solutions, we can remove V from the graph, recursively solve it, and then add V to whatever is found on the smaller input. If color 1 is allowed to appear on V, then we have to consider the situation that V gets colored 1 in the solution. So then we can recurse on the graph with V removed. We remove color 1 from the list of all of these neighbors. This will ensure that we can safely color V with color 1 when we have a solution for the recursive instance. Alternatively, if color 2 is allowed on V, then we can remove V from the graph, also remove color 2 from the list of its neighbors, and recursively solve that. So now we have 3 recursive calls. We see what the smallest solution is that's found among the 3 of them, and that's the one that we will output. And the key thing now is the following. We only recurse on graphs G minus V. Since G was a connected graph, which in the first round only eliminated V, it means that the graph G minus V has elimination distance exactly 1 smaller, right? Each of the graphs in which we recurse can be eliminated with 1 round fewer, and hence these are 3 recursive calls to a problem with a strictly smaller parameter and a standard analysis of boundary depth branching algorithms, with a small caveat for handling this disconnected case where the parameter doesn't go down, but at least we split into separate vertex sets, shows you that this algorithm will solve the problem in a running time that's 3 to the k squared, and linear in the size of the graph. Right, so if we have an elimination sequence of k rounds, then this is the running time we get. If we combine it with the approximation for finding such an elimination sequence, then still we can solve the problem in polynomial space and a running time that's some polynomial in n times actually a linear time algorithm with a polynomial in the parameter exponential dependence. So this is how we solve the odd cycle transversal problem. Let me very briefly give you a sketch of what the ideas are in general, because this was the lucky fluke that happened for odd cycle transversal because its compression problem is polynomial time solvable. In general, if you have this elimination forest, it gives you a way to decompose the graph into pieces which are either small or belong to your target class already. We can try to use this decomposition to do dynamic programming, but then we have some issue that comes up when we want to handle the base components, which are large graphs, which belong to our target family. And then the key observation is that as long as your target family can be characterized by a set of connected forbidden substructures, that's why we had requirements on connected substructures in our list of results, then any optimal solution will not delete a large number of vertices from such a base component. Intuitively, if you would delete a number of vertices here, you could also make a solution by deleting all of its ancestors and not deleting any vertices here, because we are guaranteed that these base components themselves belong to our target graph class. And hence, the exchange argument that you get shows that the number of ancestors, which is equal to the elimination distance of your graph, is an upper bound on how many vertices opt will pick out of such a base component. And effectively, this allows us to use FPT algorithms for the parameterization by the solution size to solve certain subproblems of the dynamic program. So with some little work, we can adapt them to bootstrap basically this dynamic program and then continue combining information along the small separators in our graph. Good. Let me wrap up. I've talked to you about 3 types of results for hybrid parameterizations of the vertex deletion problem. We've developed decomposition algorithms that compute elimination distance. We have seen how those algorithms can solve the vertex deletion problem themselves, and we also have some hardness proofs in the paper. The title has "and even less" in the end of it, and I didn't want to go through it in detail in the talk, because if you've never seen treewidth, it wouldn't be very insightful. If you have seen treewidth, there is a variant of treewidth which is called H-treewidth. It was recently introduced by Iben, Ganyan, and Kwon. And you can think of it as I have a tree decomposition where I can have some bags which are arbitrarily large as long as they induce subgraphs belonging to H and the vertices in them don't occur elsewhere. There might be some additional vertices in the bag, they do contribute to the width. And then if you take the smallest over all the widths of such decompositions, then you get the H tree width. And our decomposition algorithms and our solving algorithms also carry over to the setting of H tree width. And have a look in the paper if that's something that interests you. I also have two open problems. First, we gave basically poly-opt approximations to find elimination distance. It would be interesting whether constant factor approximations are also possible. And I focused on vertex deletion problems on undirected graphs, where we have a notion of connected components, and we can use it as a termination criterion for our elimination scheme. You could also try to consider parameterizations based on eliminations in rounds for directed graphs, where the termination criterion might not be so obvious. There's a distinction between strongly and weakly connected components, but maybe there is a variant of the definition that makes sense for directed graphs, and it would be interesting to see whether you can also lift algorithms which used to be fast only when the solution is small into regions where the algorithm is fast when the number of rounds is small, but maybe the solution itself is large. And with that, I thank you for the attention, and I'd be happy to take your questions.
On behalf of everyone, Bart, it was a nice talk. Thanks a lot. If you have any questions for Bart, feel free to either unmute yourself or type your question into the chat box. While we are waiting, I have a question myself. So in the case of odd cycle transversal, how close or far away are you to linear dependence on the input size and the approximation part?
When it comes to the building of a bipartite elimination force, what we do basically is first define this contraction and then call a subroutine to approximate treedepth. And already in the part where we call the subroutine to just approximate treedepth once, we're not linear. This is a subroutine by some Polish authors, including Marcin Piliczyk, if I'm not mistaken, and we didn't want to open up that black box, so that we haven't. Then there's the additional step where you need to get to basically the coloring of the graph to define what your contraction will be. And for that, we invoke the subroutine for the separation problem multiple times. So also there, naively, we would get a factor n over n. So those are two obstacles in the way to get a linear dependence.
Okay, but for the first one, well, you could try and use the linear time exact FPT algorithm. It shouldn't, I mean, it will blow up your approximation factor, but if you eventually wanted to solve odd cycle transversal, parameterize the elimination distance to bipartite graphs overall in linear dependence, maybe that could
True. So the sketch I gave you was from the viewpoint that you were shooting for a polynomial time and linear algorithm. If you allow yourself exponential in the parameter and linear, then yes, you could use the exact algorithm for treewidth instead, but there would still be the obstacle that we call the separation subroutine multiple times.
Thanks, Bart. If you have any other questions. Okay, I do have one comment though before we go. So you mentioned earlier that you would bet 100. Was it 100 euros?
Yes, I think that's a better deal than pounds.
That there is a natural implication that being able to solve the problem in FPT time parameterized just by the normal standard vertex deletion would imply that you can do it also parameterized by elimination distance. So I should note that there is some recent work by myself and a bunch of other people that shows that as long as H has some relatively gentle properties such as expressibility and monadic second order logic and a few other things, then your statement is indeed true. So your money is reasonably safe.
That's great to know. I had inferred that there was recent work when I saw the list of soda accepts, but is the paper accessible somewhere?
Well, I can send it to you, but yeah, so there is a simpler version of it on Archive where we only do it for topological minor free graphs, but the new paper does it for in more general settings.
Very nice.
Okay, so I don't see another question. So thanks a lot for joining us. So look forward to seeing you all next term. So Merry Christmas and a Happy New Year till then. Thanks a lot, Bart, for the very nice talk.
You're welcome. Happy holidays.